dive into the topic of the drivers and the software, because our lenses, they always need to be actuated, and there are a few nice ways to do it. So mainly today there are two products that we can use off the shelf, which is the Optotune lens driver 4, and then from Gardasoft the TRCL 180. Both of these drivers, they do very similar function. They both have current controller inside. They control the current through the coil, and with that they control the optical power. The main difference between the two drivers is the interface. So step by step, here we have a current range of minus 290 to plus 290 milliamps. This is enough for driving our lenses, although the EL16, for example, can take more current. So the EL16 could actually go to 400. So if, for example, with our spec, we say minus 2 to plus 3 diopters, it's with a current range from minus 250 to plus 250. Usually you'll get a little bit more than that, okay? So the specification is conservative. But minus 290 to plus 290 maybe gives you minus 3 to plus 4, let's say. And then if you go to 400, you can get maybe a little bit more. So minus 4 to maybe plus 5.5. So you still get about 30% more tuning range if you can go to full current. And our driver cannot output anymore, but the Gardasoft driver can do that. So if a 5D lens is not enough, then maybe with the more power on the driver, you can get a bit more range. In terms of resolution and accuracy, they're pretty much the same. The latency, here is relevant, the focal power mode. It's very fast. In the case of our driver, there's a few milliseconds delay, because again, our microcontroller is not that fast. So it's a little bit faster to work with this driver here. And the main difference is the interface. We provide the USB 2, which is very easy in the sense that you can just plug in. The driver will take the power from the PC, so there's no need for external power supply. This is also the reason why we cannot go higher in current, because we are powered by the computer. And you can just plug in, Windows has a driver which usually works very well, and you can run everything from a laptop. It's quite simple. But for industrial purpose, sometimes the USB is not so good. So many customers like to work with a gigabit Ethernet or use the analog interface. And actually, the analog interface, 0 to 10 volts, is very well programmed for the Gardasoft controller. So you can use it to have this kind of closed loop control where the lens follows the analog voltage. But you can also use the analog input as a trigger. For example, you can program a waveform, like maybe a step function, or maybe a triangle, or a sawtooth wave. So, and then that waveform can be triggered each time the analog input gets a trigger signal. And that's how you can actually synchronize our lens with a camera or with some other light for image stacking. So in one of the demos I'll show you later, we have a sawtooth pattern, and the trigger comes from the FPGA, which controls also the camera. So the lens always starts at the same trigger, so you can synchronize a waveform when the driver is not the master, like the slave. So if the trigger comes in from the camera or from the PC, then the lens can follow that signal and be synchronized by using the input trigger to start the waveform. Then, in terms of SDK, we just provide C# sample code, and there's a LabVIEW SDK which we can provide. For Gardasoft, there's a bit more. They have their own SDK. There's source code for more languages, so there's a bit easier maybe to integrate in the software. And important also, the supply voltage of the Gardasoft is 24 volts, so you need an extra power supply for that. Now there's also a next generation driver which is being worked on right now. So here's the first PCB version. Actually, the driver in the middle here, you see this small part? This is the size of the important part of the driver. It's 20 by 15 millimeters. And the idea is that this is now for OEMs who require the driver to be integrated in their housing, low cost. And Gardasoft is willing to license this kind of driver to OEM customers. The license model is not quite fixed yet, but maybe something like a flat fee, depending a bit on the volume. You have maybe some flat fee to pay. But then we can have the quality of, actually the same quality of the large driver, the same features in this little driver. And so it has the focal power mode with temperature compensation. It has the same waveform options and the analog input option. And the interface to control it is mainly I2C as a digital interface, or the analog in stays the same. So this is something which maybe on the bill of material for the customer should maybe be only like $10–20 bill of material to put this driver inside. But then there's a bit of an extra cost for the license fee, because then the customer doesn't have to develop his own code. He can just use what's been done. And Gardasoft will continue working with Optotune to understand how to improve the driver of our lens, like the soft step function to reduce the response time, and some other like temperature compensation. And we can then work with Gardasoft to keep improving, and the customer doesn't have to bother to learn how to do that. So one important part of driving our lens is the focal power mode. We call it focal power mode. It's a bit of an Optotune word creation. Basically, it means that we control the optical power of the lens in diopters, and the driver will calculate what is the best current to output to the lens to get the necessary optical power. So I'll draw a bit how this is done very roughly on the whiteboard. So we for each lens we measure for different currents, we measure the optical power in diopters. So we already know now we have the -2 to +3, for example, for maybe up to 250 milliamps. This is the EL1640 typically. Now, when this is measured, for example, at 30 degrees Celsius. So one line of measurement is at 30 degrees, and then we heat up the lens and we measure again. So maybe here it will be at 45 degrees. And what we know is that there's going to be an increase here in optical power. So when the lens heats up, the liquid expands, pushes more into the convex shape. Yeah, so you have expansion. This will go up further, and then you have a positive shift, and this positive effect is stronger when you are at. Actually, I did it the wrong way around. I'm very sorry about that. It's more like this. This shift up is stronger when we have negative powers and is less strong with positive powers. That's because when you have a positive lens actually when the heat increases, the refractive index goes down. So you have a counterbalance. The liquid expands and it goes up, but also the refractive index goes down. So this will balance a little bit. So actually, the temperature effect is a bit less on the high currents or the high optical power. But this is not so important to understand. Important to know is that we have these measurements here, several points, and these points are saved in the EEPROM data on the lens. So we put both curves into the EEPROM, and now if somebody wants to access, for example, I don't know, 2 diopters, and you want to go here, and the temperatures maybe between 30 and 45, maybe 35 degrees, then the controller will calculate based on these points of the calibration data, will calculate what kind of current do I have to output. Okay, so we will not discuss the calculation, but based on the calibration data and the temperature that we can read from the lens, if somebody wants to go to specific optical power, the driver will calculate what current do we have to output, maybe 75 milliamps. Okay. And actually, you can monitor this on the driver. If you plug in a cold lens and you start operating, you can go to maybe high current, maybe you go to 3 diopters, and you see the current is maybe 200 milliamps, and then you wait for 10 minutes. The temperature will go up, maybe 5 degrees. It will go up, and then the 3 diopters will stay, so your image stays in focus. But if you then check the current, it will go down from 200, maybe goes down to 180. So there's the real-time compensation of the temperature change by the driver. And so principle is we measure the wavefront quality and we measure this optical power versus current characteristic of each lens. During production, we save the calibration data onto the lens. The driver can read out the temperature, and at the beginning when you connect the lens, it will read out the calibration data. And then if you want to set a command, you do not set the current, because that would be not compensated. You set the optical power in diopters. And when you do that, then the driver will be automatically compensating the change of temperatures. Okay? Now, the typical accuracy we achieve is in the order of 0.1 diopters. Now, it depends on your depth of field, it depends on your optical configuration, whether these 0.1 diopters are a good or a bad value. So, for example, if you're in front lens configuration where you have a lot of optical leverage and you maybe have a long focal length and a low f number, you have a very small depth of field, then maybe the 0.1 is not precise enough. So if we talk again about this 50 millimeter lens, if we have the lowest possible f number, maybe the repeatability, if you're with a very small pixel size, yeah, you have a very small depth of field, the 0.1 you can maybe see a little difference. So then the solution would be to increase the f number if possible. Also note that this is kind of the worst case. This is for large steps and big temperature ranges. Usually you'll be better off than the 0.1. But for example, if your lens is at the back, like with this custom designed Kova lens, which is back lens configuration, right? So, or also the other back lens configuration, even if it's the 50 millimeter lens. When you're at the back, we learned this morning that you have less optical leverage. So the diopter change that you make is not so visible in the result. So you have maybe a factor 2 less sensitivity. And so in back lens configuration, usually this here is well within your depth of field. But this has to be tested, tried out. It's easiest to just understand whether the repeatability is good enough or not. One quick comment to the cables. We often get the question, how long can the cable be? Because you have maybe a robot which has a long arm or something far away. So officially, we specify the 5 meters for USB. This is according to the USB 2 standard. And we always ship a 1.8 meter cable with our driver. That's by standard what we include. It can go up to 5, no problem, but you should get a good cable, yeah, not like a high quality cable, because if the cable has a low quality, then the resistance is too high. What happens is the 5 volts that you have from the computer, by the time it reaches the driver, the 5 volts, they drop a little bit. So if you only have 4.5 volts, you will not be able to get the full 290 milliamp. Yeah. So that's why the USB cable has to be good quality and not too long. Now we've tested 10 meters. Basically it works, okay? But we don't give any guarantees for 10 meters because maybe if there's some interference or in general you will have a bit less performance, less current output because you waste a bit of the power over the cable. Then on the high-rose cable side, what's important here is we need to read out the temperature sensor. That's over I2C. Now, I2C is inter-IC communication. Usually, I2C is used on a PCB to talk from one component to the other. It's usually not used across the cable. But actually, I2C has, it depends on the capacity of the cable, whether it works or not. So we provide high-quality cables which are shielded, and we have tested up to 10 meters of cable, so we get the full performance, but you need a high-quality cable, and then you can go to 10 meters. Okay. So in the early days, we specified 3 meters because it's according to the I2C standard, but today we also sell 5 and 10 meter cables because we find that actually it works quite well. Of course, if somebody has a very high EMC environment with maybe a lot of machines, you better test first if it works. But so technically 10 meter and 10 meter USB, 10 meter high-rose could be the longest cable. But if somebody needs to have like a very long cables, maybe for traffic applications, you know, or for tunnel TV, yeah, something that goes in the tunnels, then it's better to maybe work with the Gardasoft driver and use an Ethernet cable, because then you can go easily 100 meters of length. But then you need to have a power supply at the driver side. Now there are 3 ways to basically find your focus. Image-based is autofocus, so you use your image as a closed loop. Yeah, this is the typical autofocus you get from your phone. If you both nowadays all the cameras have autofocus lens, so the camera takes multiple pictures, finds the best picture, goes back to where the best picture was. So this takes typically 10 to 15 frames to find the best focus. Now, if our lens, basically we can do that within like 20 milliseconds each. So in theory, you could say maybe after 200 or 300 milliseconds, you can do an autofocus. Maybe in practice, it's a little bit more, but definitely faster than 1 second, you can do autofocus. But of course, it's not completely reliable, because if you focus on a white piece of paper, chances are good you don't see any contrast, and then you see nothing. So if you do maybe you know, defect detection on a glass, if you do autofocus and you don't find any defect, you're never sure, did I not have any defect, or did I just not find the right focus? So it's only good if you have maybe a human feedback to make sure it's correct. So what's more common in industry is the preset lookup table. So you know, basically there's maybe 3 products, A, B, and C, and the PLC system or the computer knows which product is coming, and then there's a very simple lookup when there's product A, maybe 2 diopters, product B, maybe 1 diopter. So you just choose the right diopter setting because you know what's coming. So this has to be pre-programmed. And they're typically, these lookup table is in the software or in the PLC that runs the machine. And the benefit is here very fast focus time, so only one jump is needed. So roughly 15 milliseconds, you can jump to the right position. But we have to then offer the repeatability, the high repeatability. So this calibration has to then remain working for maybe several months or years. That's why we then need definitely this temperature compensation to make sure that we don't lose the calibration here. And then with the distance sensor, it's kind of the same thing as over here, but except the PC or the system does not know what's coming, like maybe the package sorting in logistics, you have different boxes. So the computer does not know what's coming, but the sensor is going to give a signal that can be related to the optical power. So here the lookup table is basically different distances have different diopter value, but actually if you use the analog in, instead of distance, you have here actually a voltage. And you do a lookup table from a voltage to the optical power. And that's exactly what the demo does over here. Yeah, there's an autofocus implementation in our own software. So we've used the IDS SDK to include the UI viewer. So if anybody wants to use IDS cameras with our software, this works actually quite nicely. We can then also do that again on the demo. We've implemented the autofocus with 3 steps. So first step, you increase the current, and the contrast value is read out of the image. So we use a Sobel filter to get the contrast number. And maybe it starts blurry, and then it gets better and better and better. And at some point, it goes down again. Maybe it goes down twice, and then when it goes below this threshold, the algorithm goes backwards. So you go up again, smaller steps. When it goes below the next threshold, it stops. It goes forward again and takes very small steps, and then you will find the best focus. This is just one way of writing autofocus code. It can also be, doing all the steps in one direction, and then you basically get the curve like this. What you can usually do in the focus is a fit parabolic. So if you do this stepping and have multiple focus values, it maybe looks like this here. So this was the best focus value that you got in a picture, but maybe it's not the best overall. That's why we usually take them smaller steps in our case. But what you can also do is you can fit a parabola curve through here, and then if you have a parabola, you can find out where is the 0 point, the maximum of the parabolic curve, and then usually here is going to be the best focus, right? So in this case, maybe the point that we had here is not the absolutely best focus value, but the 0 point of the parabolic would be your best value. So this is a different approach. Maybe this is how they do it in mobile phones, I don't know. But that's quite a nice way to do it as well. Then here's a summary of the demo with the distance sensor. We talked about that enough by now. So I think after we finish the presentation, as a next step, we will go and look a bit more details how these 2 drivers actually work. And I'll try to do that on the screen so everybody can follow. So with our driver, we have a serial protocol that everybody can implement. So we have the USB communication, right, which pops up in Windows like a COM port. In Linux, you have a certain, like a file name, where you can read and write to that file name. So in both systems, you have a serial communication. And the commands are the same for Windows and Linux. And you can use any kind of software that can output a serial command. So the very simple command is start. It actually works in ASCII, so you can type start, send, and then the driver replies ready. This is a very simple handshake just to check the connection. And then there are commands for set current, set focal power, get temperature. There's a few more commands, but these are the most important, specifically set focal power. And then, so what you typically do in the end is you connect the COM port, you send the start command, then you have to send one command to go into focal power mode. And there you actually also hand over some temperature limits, which kind of tell the driver this is the temperature range you expect to work in. And then you can set focal powers. And behind these commands, we are using a checksum. So there's this 16-bit checksum, which might actually not be so necessary because the USB communication is actually very reliable. But we didn't know that at the time, so we included this checksum. It's not a big deal. We have source code how to add the checksum at the end of a command. That's about it. We have an Excel file that shows all these commands. So it's a long, big table with a lot of detail for each command. So how exactly to put together a set focal power command. And this is also described in the manual of the lens driver. Now, there are a few software people we partner with, like Common Vision Blocks from Stemmer Imaging. EVT is what we use for the demo here. It's a German company. Halken, I think most people know. Matrox has also a little, we have some source code, which is using the MIL library for autofocus, which we can share. Sankso in Hungary, they have implemented their commands. And Neurocheck, this inspection robot we saw in Germany. Envision is actually a Swiss company that has a machine vision software. So these are a few partners we work with. Probably there's nowadays even more companies that have written software that can control our driver. Slides here are about focus stacking. So the three modes I mentioned is autofocus, preset, table, and sensor mode. Actually, there's a fourth one which is missing, and that's the image stacking. So in this example here, this is a picture we took with an Optotune lens on a mobile phone camera. I just put the little lens in front of a phone, and we took, in this case, I think 15 pictures, going from focus from the front to the back. So when the lens is more convex, you're in the close working distance, far working distance, and this whole stack of images is only focused on a very small part of the image. So you can see the depth of field is, yeah, you need at least like 10 images to cover the whole object here. So taking the whole stack, putting it together to one hyperfocus image. So like here's a picture where everything is in focus. We used software called Helicon Focus. It's available from the internet. You can download for $100 or something. And it takes these pictures and puts them together, calculates this image, which has a very nice everything in focus picture. And as a byproduct, you also get the depth information. So basically the black is more in the front, the gray light is more in the back. So you can get 3D data out of such a stack. And the thing is now this software takes about 15 seconds to do that. It's a high resolution camera, so 15 images of maybe 12 megapixel each is a bit slow. It takes 15 seconds. For somebody who's like a photographer, it's no problem. He can wait a few seconds, it's no problem. But if somebody wants to use this in industry, it's too slow. So we are trying to work with some software companies to make the stacking go faster. Now, Silicon Software is a German company who does frame grabbers. Their frame grabbers have a pretty fast FPGA on it. And they did with us a little demo. There's actually a YouTube video if you want to look at that as well. The point is that the The FPGA sends a trigger signal to the Gardasoft driver 20 times per second. So every 50 milliseconds, you get a trigger. The Gardasoft driver makes a sawtooth waveform. So within 50 milliseconds, the lens goes across its whole tuning range, back to 0 and goes again. And the high-speed camera selects for each stack 20 pictures. So it's running at about 400 frames per second. And you get then within one stack of 50 milliseconds, you get those 20 pictures. And the FPGA is able to do this extended depth. The FPGA can do all these calculations at the same speed as we're acquiring the pictures. So basically what you get is an output of like an all-in-focus picture is output at 20 frames per second, maybe over gigabit Ethernet can go to the computer. So what the frame grabber does is it pre-computes all the stacking before it goes into the next system. And that can be pretty fast. So we're not quite happy yet with the quality of the result because the algorithm still has to be improved a bit. The images look a little bit noisy, but it's something you can still improve. So if we have time, we will work with Silicon Software to make this better. But the question is actually, where can we use this kind of application? Because it's also not quite cheap. You have a high-speed camera, you have a frame grabber with FPGA, so you'll need a few $1,000s of budget to get all these components. So we know that in the microscopy, in microscopes and in research, there's definitely an interest to do stacking. A lot of people in biology, they do stacking of cells that they image, and maybe for industry, if you have a very high-speed throughput, like mobile phone inspection, where you have a very high cycle time, very short cycles, you have to maybe take pictures at multiple levels, but you don't have time to wait 20 milliseconds for our lens to change focus. But if you do a scan, you can get all these pictures at once. So maybe I could see that in the high-speed manufacturing, this could be interesting. But if you go down this path, you definitely need to understand something about FPGAs and programming. So it's not an easy thing to sell. You need to have a lot of application know-how to make this work. So, but this is, I think, for the future, something we see as an interesting, ongoing development to make stacking easier for customers and more useful. Okay, so this is the chapter on drivers and software.